So in the last session we discussed operators like gradient, divergence, curl, and then we have seen the properties of it. Then we defined what is a conservative vector field, and we worked on how to find the corresponding scalar field for the given conservative vector field. So that's what we did. And let us move to the line integrals. Line integrals where you need to integrate the conservative vector field. See, generally this is how we write line integrals. Integral along C, you will be given with some curve that may be a closed curve or maybe a curve like this. So this is a closed curve. Second one is a closed curve, whereas the first one, it's not a closed one, it is a curve from one point to another point. So now you will be asked to integrate some function that may be a scalar function or a vector function, x, y, z into ds, and integral along C, f bar into ds also can be asked, but mostly this is what you'll find, f bar into dr bar. Yeah, sometimes you may have this f bar dot product with n cap into ds. And did I talk about directional derivatives in the last class? I think I didn't solve any problems on directional derivative, just I mentioned how to find. Let me do one thing. Let me just quickly tell you how to find the directional derivative, and later I'll move to this line integrals. So directional derivative of f in the direction of u. Okay, so we are going to denote it like this: du of f at a, b, c, which will be given by gradient of the function at this point dot product with u cap, where u cap is the unit vector. See, for example, you are given with a function f of xyz equal to xy plus 2x square yz. This is the function, and you ask it to find directional derivative in the direction of I minus j plus 2k. This is the direction vector. What do you do? First you find the gradient. Gradient of f is nothing but y plus 4xyz, and derivative of this with respect to y, which is x plus 2x square z j plus, and this will be 2x square y into k. Okay, so this is the directional derivative, gradient of the function. And you know what is u bar, so let me find u cap, that is I minus j plus 2k divided by its magnitude, that is square root of 1 plus 1 plus 4, that is root 6. So when you take grad f dot product with u cap, so ith component here multiplied with the ith component here, so 1 by root x is common, so this is 1 by root 6 is common, this is y plus 4xyz, this is the first term, 1 times of this, minus of x plus 2x square z plus 2 times of 2x square y. So this is the directional derivative in that direction. If you want this derivative at some particular point, let's say I want the derivative at 1, 1, 1, then what do? You simply substitute 1, 1, 1 in place of x, y, z. So this will be 1 by root 6 into 1 plus 4 minus 1 plus 2 plus 2 times of 2. This will be 1 by root 6. When you simplify, 5 and 2 plus 4, this is 6. So which is root 6? So root 6 is the directional derivative of f at 1, 1, 1 in the direction of u. Okay, so this is how we find the directional derivative. And sometimes you may be asked to find directional derivative in the direction of normal vector. So let us see how to find normal vector using the gradient. Normal vector of a surface which is given by f of x, y, z equal to k. Let's assume that the surface equation is given by f of x, y, z equal to k. Or you can write it as z equal to, or sometimes we can write z as a function of x comma y. This is how also you can write. Okay, you express it in any way. Then, so normal vector is nothing but gradient of that function. So gradient of f will give us the normal vector to the surface, which is nothing but dou f by dou x I plus. Okay, so this is the normal vector to the given surface if the surface is represented by f of x, y, z equal to k. And if you want unit normal, you're going to divide with its length. And these normal vectors are useful to find the angle between two surfaces. Let us say you're given with two surfaces. Two surfaces are given. Let's assume phi 1 equal to k and phi 2 equal to c. These are the two surfaces. Now these two surfaces are intersecting at P. Okay, phi 1 and phi 2, or let P be the point in the intersection of phi 1 and phi 2. Now I'd like to find what is the angle between these two surfaces at P. Angle between phi 1 and phi 2 at P, that will be given by theta equal to gradient of phi 1 at P. It means the normal vector of phi 1 at P. So this is what, or let me write it as n1 dot product with n2 divided by magnitude of n1 into magnitude of n2. So this is what will give us cosine of the angle, cos theta. But if you want exactly theta will be given by cos inverse of n1 dot product with n2 by their magnitudes, where you can see what is n1. n1 is nothing but gradient of phi 1 at P, and similarly n2 here is gradient of phi 2 at P. So this is how you can find angle between two surfaces. All that you need is normal vectors to those surfaces. Once if you know the normal and if you see the angle between the normals, you can say that that is the angle between the surfaces. And I'd like to mention a small point at this directional derivative. If you want to see what is the maximum rate of change, or if you want to know what is the direction in which the function has maximum rate of change, so that direction is nothing but normal vector direction. It is nothing but gradient phi. So you can write a note. The note is that directional derivative is maximum, or directional derivative of f is maximum in the direction of gradient of f. Okay, and if you want to see what is the maximum rate of change, which is nothing but absolute value of grad f. So absolute value of grad f will give you the maximum rate of change, and the direction is nothing but gradient of f. If you want to see the minimum rate of change, you can simply take negative of that gradient direction. So the fastest increase and the fastest decrease. The fastest increase happens in the direction of grad phi, whereas the fastest decay happens in the direction of negative grad phi. And if you want to see the minimum rate of change, that is negative of absolute value of grad phi, grad f. Okay, so this is about directional derivative. You can find some questions on finding directional derivatives and the maximum rate of change, and the direction of maximum rate of change or the minimum rate of change. Similarly, finding angle between the surfaces using the normal vectors, or finding the normal vectors of surfaces. So you can find some questions like this. Okay, so now I hope you can understand what do I mean by a normal vector here, n cap. So if you have a surface, you take the gradient of that surface, which gives you the normal vector. So f bar dot n cap into ds. Okay, so here in the line integral, when you write ds, which actually represents the length of a small arc, this is what ds mean. Now this ds is going to be replaced with, we know formula for arc length. So dx by dt whole square plus dy by dt whole square into dt. Suppose if you write y as a function of x, if y is a function of x, then this is what we write in place of ds, that is 1 plus dy by dx whole square into dx. Whereas if you know x as a function of y, then we'll replace this ds with 1 plus dx by dy whole square into dy. Okay, so this is what you need to replace in place of ds. So this is what about the first integral. So first you parameterize the curve. The parametric representation of the curve can be written like this: a function of t, and y as a function of t, and similarly z as a function of t. Okay, if you have 3 variables, yeah, you'll have one more guy here. Let me write. Suppose if you take a curve in a 3-dimensional space, you can have this formula. Okay, but here you cannot say that y is a function of x comma z. You cannot say this. But what you can say is y is a function of x and z is also a function of x. That's what you can say. Maximum it can happen here. Z is a function of x. So in that case, you'll have dou z by dou x, dz by dx whole square as well. But mostly whenever you have a curve in 3 dimension, you better parameterize it in this way: x of t, y of t, and z of t. Okay, so these two formulas are for the curves in 2-dimensional space, whereas this one is for the curve in you can take in 3 dimension as well as in 2 dimension. But look at the second guy. You can directly write it like this: integral along c. R bar is nothing but a position vector, and which will be written as xi plus yj plus zk, because it represents the position of this element x, y, z. Now dr bar, it means its derivative is nothing but dxi plus dyj plus dzk. Okay, so now in place of dr, you can write dx dy dz, and in place of f bar, you can write f1i plus f2j plus f3k. So when you take the dot product, now you will be left with this: f1 into dx plus f2 into dy plus f3 into dz. Now you just write the parametric representation of the curve: x as a function of t, y as a function of t, z as a function of t. Simply substitute it here. And how about this, the third integral, f bar dot product with n cap into ds? So let me discuss it in 2 dimension. See, in 2 dimension, you know what is dr bar. Dr bar is nothing but dxi plus dyj. If you ask me what is the normal vector here, so normal vector is a vector which is perpendicular to the tangent vector. Okay, so now it is enough to write a vector which is perpendicular to dr. So that is nothing but dyi minus dxj. This is what you can write. You can see that n bar and dr bar both are perpendicular. So now in place of n cap, you are going to write this vector and you take the dot product, then you evaluate that integral. See, remember one thing: the moment you parameterize the curve and substitute it here, then line integral becomes a normal integral. And I hope you know how to solve a normal integral. Okay, I'd like to give this problem. What is integral of xy into ds, where c is the curve, c is y equal to 2x plus 1, where 0 less than or equal to x less than or equal to 1. This is what they gave. Now this is a scalar function, and you know how to write ds. Here, if you look at the given curve, given y as a function of x, so we can directly write what is ds, that is square root of 1 plus dy by dx whole square into dx. So this is same as 1 plus derivative of this with respect to x is 2 square into dx, which is actually root 5 into dx. That's it. So ds will be replaced with root 5 into dx. In place of y, you're going to take 2x plus 1. Now let's write this integral. Limits of the integral is x equal to 0 to 1. Everything we are writing in terms of x. So x into y is actually 2x plus 1. Now ds will be replaced with root 5 into dx. Now we know how to integrate it, right? So now just integrate and write the final answer. So next, the second problem, integral along C. This time let us have a vector field. Let me start with x plus y I plus yj dot dr. What is this? If C is a closed curve that is given by upper semicircle and the bottom, both were included. The upper semicircular part is included, and also the bottom line is also included. And let us assume that, see, if they do not give any direction, you should assume the curve is always traversing in the anti-clockwise direction, but because that is a standard direction everyone prefers. Anti-clockwise direction, it means this is what. Now here, if you look at C, it is not one curve. It is actually combination of two curves. One is a circle and another one is a line. So let me write it as C1, the line as C1 and the circle as C2. So now C can be seen as C1 union C2. So first you need to parameterize C1, next parameterize C2, then you try to integrate it. First let me parameterize C1. C1 is nothing but it is a line from this point. What is this point? Oh my god, I didn't tell you what is the circle here. Let me give the points here. The point here is negative 1 comma 0, and this one is 1 comma 0, and of course this is what 0 comma 1. So we have taken a unit circle here. Now C1 is a line from negative 1 comma 0 to 1 comma 0, and you can see the equation of this line is nothing but y equal to 0. Or in other words, you do one thing. Whenever you need to parameterize a line from P to Q, so this is the form. R of t equal to P plus Q minus P into T, where 0 less than or equal to T less than or equal to 1. So this is the standard parameterization for a line from P to Q. You can see that when you plug in t equal to 0, you get P, whereas when you plug in t equal to 1, you get Q. He is starting at P and ending at Q. Now R of t here is, you know what is P, negative 1 comma 0 plus t times of Q minus P. Q minus P, which is 2, 0, that's it. In other words, this is nothing but minus 1 plus 2t comma 0, where 0 less than or equal to t less than or equal to 1. So this is the parametric representation. It means you can see what is x. X is nothing but negative 1 plus 2t, and whereas y is 0. This is the parametric representation. Now let us take this line integral. Our aim is to evaluate this line integrals. First, let me evaluate it along C1. Now this is equal to integral along C1 x plus y into dx. You know what is dr? Dr is nothing but dxi plus dyj. So when you take dot product, this is what you'll have. So you know for C1 x is 2t minus 1, whereas y is 0. From this you can see what is dx, which is 2 dt, dy, which is 0. So when you plug in here, integral t equal to 0 to 1, x plus y, so that is 2t minus 1 plus y is 0. This multiplied dx, dx is nothing but 2 into dt, plus y is 0, dy is also 0. Now along the first curve, the integration is 0 to 1, you'll have 2 times, let me integrate directly, t square minus t, oh, you'll get 1 minus 1, you'll get 0. So integration along that curve is 0, along the line from 0 to 1. Why? Because you can see integration is t square minus t. When you substitute upper limit, 1 minus 1 you get, that is 0. So integration along C1 is 0. Now you need to integrate along C2. So what is C2 here? C2 is a semicircle from 1 comma 0 to negative 1 comma 0. So now what is the parametric representation of the circle from this point to this point? See, this is a circle centered at origin. Now you can directly write its parametric representation, x of t, that will be cos t, and y of t will be sin t. Okay, but we don't want the full circle. We need a circle from here to here. That's it, half part of the circle. Angle here is 0, whereas when it comes to here, angle will be pi here. Therefore 0 less than or equal to t less than or equal to pi. Suppose if the radius of the circle is k, then we are going to take k here, k. Okay. Suppose if the circle is centered at a comma b, then instead of taking x comma y, we take x minus a and y minus b. From that we can see that x is equal to a plus cos of and y equal to b plus sin of. This is how we do. But anyway, we don't have that issue. The circle is centered at origin here. Now how do you integrate it? Sorry, let's write the integral first. Integral along C2, this is x plus y into dx plus y into dy. Yeah, I should calculate what is dx. Dx is minus sin t dt, and dy is nothing but cos t dt. Now this equal to integral t equal to 0 to pi. You know what is x plus y, that is what cos t plus sin t into dx. Dx is negative sin t into dt plus y is sin t and dy is nothing but cos t dt. I hope you can cancel this negative cos t into sin t, and this you can cancel. Now you are left with minus of integral 0 to pi sin square t dt. You know sin square t can be written as 1 minus cos minus of integral 0 to pi. This is 1 minus cos 2t by 2 into dt So just integrate, integrate it. When you integrate negative 1 by 2, this is theta minus sine of 2t by 2, limits are from 0 to pi. So when you plug in the limits, you get negative pi by 2. So this is the answer. So answer to the given problem is, anyway, the value of the first integral is 0 and value of the second integral is negative pi by 2. When you add the result, you're going to get negative pi by 2. So answer to this problem, this is 0 minus pi by 2, so which is nothing but minus pi by 2. So this is how we'll directly evaluate the problems. But if the vector field is conservative, we don't evaluate. We'll directly write the answer. You tell me one thing, is this vector field conservative? Whatever which is written here, x plus y into I plus yj, is it conservative? Yeah, your answer is no. Yes. So it is not conservative. If it is conservative, our life will become easy. See, if the vector field is conservative, then the line integral is independent of path. When it is independent of path, here you have a closed curve, so the value will become 0. Answer will become 0 if it is conservative. But it is not conservative. Anyway, I cannot apply that. But let us see what happens if f bar is conservative. Let's see if you have integral along C, f bar dot dr. This is what you are asked to evaluate, and you are given with f bar which is conservative. F bar is conservative, it means what? F bar can be expressed as gradient of phi or gradient of some function f, isn't it? Now f bar can be replaced with this. So integral along C, f bar dot product with dr can be written as integral along C, gradient of f dot product with dr. But gradient of f dot product with dr, which is exactly derivative of the function. Okay, let us assume that C is a curve which starts at P going till Q. Now I am going to write it like this. This is integral P to Q derivative of f. But we know integral of derivative of f, which is same as f. Okay, so now this is what f, let me say f of something, f of xyz, where the lower limit is p and the upper limit is q. So finally the answer is f of the final point minus f of the initial point. Okay, so now if the line integral is if the vector field is conservative, then the line integral is independent of path. So the final answer, it depends on the starting point and the ending point only. Means you can directly say that when f bar is given by grad phi, then integral along C, f bar dot dr, this is nothing but phi of q minus phi of p. Okay, to avoid confusion, let me write f only. Grad f, this implies this is f of q minus f of p. Or in other words, we can write a note, if f bar is conservative, this implies line integral is independent of path. And of course you should ask, what is that line integral? What is there in the line integral? So the line integral in this form, that is integral along f bar dot dr bar, this is what is independent of path. I am not talking about every line integral. Integral f bar dot dr is independent of path. Let us see an example. Let's say I am giving a curve and you are given with some integral here. The integral is x plus y plus z into dx plus, now here x plus 2y into dy plus, now this is x plus z plus 1 into dz. What is the value of this integral? If C is a curve from 0, 0, 0 to 1, 1, 1. So I need value of this integral. If C is any curve, okay, it can be any curve from this point origin to 1, 1, 1. If they say any curve, you can take a line as well, line from 0 to 1, 1, 1. But if the vector field is conservative, no need of taking any curve. First let us see whether the given vector field is conservative or not. Can you verify and tell me whether it is conservative or not? Yes, correct, it is conservative. Why? Because if you see the scalar function, you can directly see what is the scalar function. Is it conservative? I have x, so f of xyz is x square by 2 plus x into y plus xz. So this was taken care and this was taken care. Now plus y square, this is done, plus z square by 2 plus z. So this is the function. Now answer to the problem. So integral along C, f bar dot dr bar, which is nothing but f of 1, 1, 1 minus f of 0, 0, 0. Now what is the answer? So answer is nothing but 1 by 2 plus 1 plus 1 plus 1 plus 1 by 2 plus 1. Total 4, 5. Okay, minus 0. So this is nothing but 5 minus 0, which is 5. That's it. So if f bar is conservative, our life is very easy. It is easy to evaluate the line integral. You see this question, it is very easy. You need to find this constant so that this vector field becomes incompressible. When do you say a vector field is incompressible? When its divergence is 0. When divergence of V is 0, then we say it is incompressible. You calculate what is its divergence. Divergence is nothing but you can see 10xy plus cy, so this is c minus 10xy. These two get cancelled. So if you want this to be 0, definitely c must be 0. So option B is correct. That's it. Very easy. 1 mark. This question is from GATE 2021 chemical engineering paper. Okay, next let us look at a question on line integrals from ECE. I hope it is visible. The vector function f of r is given minus xi plus yj. This is the function they gave, and you can see that this is a conservative vector field. And if you ask me what is f is nothing but minus x square by 2 plus y square by 2. This is what f here. And our given vector field, this is nothing but gradient of f. Anyway, they are asking the line integral of f, that is integral along C, f bar dot dr. They are asking what is it. And you try to observe, C is not a closed curve. They said defined over a circular arc C as shown in the figure. You see an arrow mark is there here only. It is not given here and here. Suppose if the arrow mark is given here and here, then you can assume the given curve is a closed curve. No. Here if you observe that the given curve is only this part of the curve. You see what is the starting point. The starting point is 1, 0. And you see what is the ending point. When it makes an angle 45 degrees, and what is this point? This point is cos of 45 degrees, sine of 45 degrees. And we know their values, that is 1 by root 2 and 1 by root 2. So therefore the starting point is 1 0 and the ending point is 1 by root 2 and 1 by root 2. Therefore what is this? This is equal to f of ending point, that is 1 by root 2 comma 1 by root 2, minus f of the starting point, that is 1 comma 0. So when you substitute ending point here, 1 by 2 into 1 by 2 is common, right? Y square, that is 1 by 2, minus x square, which is 1 by 2, that will become 0, minus of 1 by 2 into minus 1 square plus 0 square. So finally you get 0 plus 1 by 2. Therefore 1 by 2 is the answer. Okay, and let me show you the options. Okay, so 1 by 2 is correct. Let us look at one more question. Now this question is from Civil 20 paper. C represents the line segment from 0 0 0 to 1 1 1. Now what is the value of this integral? So they didn't give any option. They wanted us to write the direct answer. So whenever you see a line integral this way, check whether the vector field is conservative or not. So first, if I integrate the first expression, I get xy plus xz. Okay. And if I integrate, this is what f1, let me say, and f2, integrate the second expression with y. So when you do that, you'll get xy plus yz, and f3, that is xz plus yz. Yes, xy, you should write it only once. So f equal to xy plus, next xz and xz, you should write it only once, xz plus, so the next one yz. So therefore f bar is conservative and the corresponding vector field is nothing but this xy plus xz plus yz. Therefore answer to this problem is nothing but f of 1 1 1 minus f of 0 0 0. So this is what exactly 1 plus 1 plus 1 minus 0, which is 3. Therefore answer to this problem is 3. Okay. And similarly, every time you can find a question on directional derivative. May not be for I cannot say that this question will be asked for this branch. But on conservative vector field, among the 6 branches, at least you can find one question. Similarly, on a directional derivative, you can find one question. Okay, but you should make sure about everything, because we don't know which question is going to come in your paper, right? See, there is a question on directional derivative in mechanical 20 paper. So given a function, and at this point they are asking us to find the directional derivative in this direction. So you know the direction. So the direction is 1 plus 1 minus 2i, I minus 2j plus 2k. Now you know the function. What do you do? First you find grad f. Gradient of this function is yz I plus xzj plus xyk, and they want it at this point. So gradient of f at negative 1 1 3. So if you substitute it, yz, so this is 3i minus 3j minus k. This is grad f. Okay, now let me take dot, let me see what is u cap. This is I minus 2j plus 2k divided by its length. Okay, so now when you take the dot product, 1 by 3 is the length. So 1 into 3, 3 minus 2 into minus 3, that is plus 6, and minus 2 plus 2 into minus 1, minus 2. So I get 9 minus 2 by 3, so I got 7 by 3. Therefore 7 by 3, this is the directional derivative. Okay. Now you see, this is a question in 21 paper, civil engineering. Unit normal vector to this surface at this point 4 4 4 4. It's supposed to be given like this. Some bracket should be given. So what is a unit normal vector? So what do? You need to take gradient of f, and you need unit normal, so magnitude of gradient of f. This is what you need to do. So first you find what is a normal vector. This is 2xi and 2yj and 2zk, isn't it? And dividing with its magnitude, that is square root of, 2 can be taken out. You'll get x square plus y square plus z square. 2 can be cancelled, so in the numerator you have x, y, z, whereas in the denominator square root of x square plus y square plus z square. But you know what it is? It is actually equal to 48. And you substitute this point 444. When you do that, 4 divided by, root 48 can be written as can it be written as a multiple of 16? Is it nothing but 16 times 3? Right. So if it is 16 times 3, so this can be written as 4 root 3. So 4 divided by 4 root 3, 4 divided by 4 root 3, 4 divided by 4 root 3. 4, 4, 4, 4 cancel. So the answer is 1 by root 3, 1 by root 3, 1 by root 3. So that is the answer. Unit normal vector. And this question is for ECE students. Gate 21. Given a vector field and one unknown is given, C1 is an unknown. Now given that f bar is irrotational, or they are saying conservative, both are same. If f bar is irrotational, what must be this C1? Then what is the condition? If f bar is irrotational, then definitely curl of f bar must be 0. Or of course, without going for curl f bar, you can directly tell what is C1. See here, you can see z. You have z, so the corresponding term definitely will be here. Okay, so this is the coefficient of I, and you have z, and you have nothing here. How can it be conservative here? Is there a printing mistake? So if you have minus C1 into Z, then definitely this will become X, and minus C1 into X will be there. Let me take the exact question from the paper. It is correct only. Minus C1Z you have, and here you have 2y plus Z. F bar is irrotational. Then what must be that constant? That constant must be 0. That must be 0. Why? Because I'm not finding any term here. I'm not finding any term which involves x. Okay, and let me see what is the corresponding scalar function. The scalar function is going to be 4xy. So 4x, which was taken care, and here you have 2z, so definitely you'll have 2yz plus z square by 2. That's it. So C1 must be 0. Okay, even if you do it using curl, you'll get C1 equal to 0. There's no doubt in it. See, they gave it as conservative. It can be conservative only when the curl f is 0, or in other words, we can do it by inspection. Since you have z here, x ఉన్న టర్మ్ ఇక్కడ ఉండాలి. ఇక్కడ యాక్చువల్లీ x ఉన్న టర్మ్ లేదు అంటే దాని అర్థం ఏంటి, అక్కడ z ఉన్న టర్మ్ కూడా లేనట్టే కదా, అంటే C1 must be 0. Okay, but let me do it using this curl f bar. Curl f bar is nothing but ijk 4y minus, okay, I should write dou by dou x, dou by dou y, dou by dou z, and this is 4y minus C1z, this is 4x plus 2z, this is 2y plus z. Now this is equal to I times, you can see, which is 2 minus 2 gives you 0, minus j times, this is 0 minus 0, 0 minus C1, 0 minus C1, maybe positive C1, plus k times, this gives you 4 minus 4, 0i plus c1j plus 0k. So this can be 0 only when c1 equal to 0. So therefore c1 must be 0. Okay. You see, for calculating curl it took some time, but if you observe it directly, it takes just 3 seconds. So let me discuss what are Green's theorem, Gauss divergence, and as well as Stokes theorem now. So first let us start with Green's theorem. Let's say you have some curve, a closed curve, which traversed in anticlockwise direction and which encloses some region R. Then Green's theorem gives us the relation between the double integral and the line integral, and the relation is nothing but integral along C f of x comma y into dx plus g of x comma y into dy. This will be equal to double integral over R dou g by dou x minus dou f by dou y into dA. Integral along a closed curve. Here you should have some assumptions. Assumptions are that f and g are very nice functions. Nice, I mean they are continuous and they have partial derivatives. They are continuous and they have partial derivatives. Okay, so for example, let's say you are given with a triangle. This is the triangle you have. Let's say the vertices are negative 2 comma 0 and 2 comma 0, whereas this point is, let me take 0 comma 3. Okay, now this is the triangle you are given with, where curve is nothing but the boundary of this triangle. This is what our C is. Now you are asked to evaluate 2x square plus 5y into dx plus y square plus sine of y minus or plus 7x plus 1 into dy. So you are asked to evaluate this integral along this curve where C is given here. Now using this Green's theorem you can directly evaluate it. See, it is in this form, integral f dx plus g dy, where f and g are very nice functions and C is a closed curve. You can see that C is a boundary of a triangle. This is a closed curve and which encloses this region. Now using Green's theorem you can say this integral equal to double integral over R dou g by dou x minus dou f by dou y. So all that you need to recognize what is f here and what is g here. So first you see what is dou f by dou y. What is dou f by dou y? Derivative of f with respect to y, 0 plus 5. Next, dou g by dou x, that is 0 plus 7 plus 0, but anyway 7. Now you can see dou g by dou x minus dou f by dou y, which is nothing but 7 minus 5, which is 2. Now integral along C, f dx plus g dy, that is equal to double integral over the given region gx minus gy, that is 2 into dA. Okay, I simply substituted dou g by dou x minus dou f by dou y with 2. Now this is nothing but 2 times of this integral represents exactly area, so area of R. But we know what is R. R is a triangle and we know formula for finding area of a triangle, half BH, half into base length is nothing but 4, whereas the height is nothing but 3. Therefore answer to this problem is 12. Therefore the value of the line integral is 12. That's it. Okay, now let's find how to find area using Green's theorem. So that is nothing but area using line integral. Okay, so it will be given by this formula, integral of 1 by 2 into, see, the simple thing is, we know double integral over r into dA, which represents area, right? Now here, in place of dou g by dou x minus dou f by dou y, I have 1. If I get 1, then it represents area. So now you try to choose f and g in such a way that dou g by dou x minus dou f by dou y is 1. Okay, if you choose such, then this line integral will represent the area. Okay, right now I'm going to take this. I'd like to take f equal to y and g equal to x. If I do that, fy will be 1, gx will be 1, but both will get cancelled. Gx minus fy will give me 0, but I don't want 0, so I'll take negative y here so that I get negative 1. So gx minus fy will give me 2. So here I'm getting 2. Let me send this 2 here, 1 by 2 times. So in place of f, I need to write y minus y, negative y into dx plus, and in place of x, g, you write x into dy. Therefore, half of integral along c, x dy minus y dx. This will give you area bounded by the curve C. Area bounded by C, which is nothing but integral along C equal to integral along C. This is 1 by 2 x dy minus y dx. This is the formula. And I think in 2019 there was a question on finding area using Green's theorem. Okay, so this is what about Green's theorem. So the next thing is Stokes theorem. I'll say that the Stokes theorem and Green's theorem are same if you are on a plane, and of course the extension of Green's theorem is nothing but Stokes. See, the Green's theorem discussed that when you have a closed curve which encloses the region R, it gives you a relation between the line integral and the double integral. Now this time, instead of having a region, this region will be replaced with a surface. Okay, now you have some surface like this, and you know what is the boundary of the surface. The boundary, this surface is bounded by some closed curve. It's like a kind of cap. For example, if you take a upper hemisphere, you can see the surface, and the boundary is nothing but a circle. Okay. Now if you have a surface like this, now Stokes theorem will gives you the relation between the surface integral and the line integral. You have a surface here and you have a closed curve C here. Now the relation is nothing but integral along C f bar dot dr. The same thing, the same line integral. That will be equal to the flux of curl f, integral over this surface, curl f bar dot ds. Okay, or in other words, integral along C f bar dot dr, this will be equal to double integral over S curl f dot n cap into ds. మా ఇలా అయినా రాస్తారు, ఇలా అయినా రాస్తారు, ఏదైనా ఒకటే. Some people may write ds itself as a vector, but some people will write n cap into ds as a scalar. And when it comes to Stokes theorem, like if you are asked to evaluate over a surface, then you can shift to a line integral, because instead of working on a surface integral, it is easy to work along a line. So from this surface you directly move to the line and you do it. Okay, suppose if f bar is given by grad phi, let's say if f bar is grad phi, then from this what do you know? You know curl of f bar, which is nothing but curl of grad phi, and this becomes 0. That's it. If f bar is given by gradient function, then definitely the value will be 0. Okay. Now let me discuss Gauss divergence theorem. So the Gauss divergence theorem, which gives you a relation between a volume integral and a surface integral. Let's assume that you have some volume which is enclosed by, let me say, E is the solid, and which is enclosed by some surface S. Okay, so what you have here is a closed surface. A closed surface which encloses the volume E. Okay, now you can relate integration along the surface and integration along the curve. Sorry, integration along inside the region. But I forgot to tell you one thing. So here you can actually see like the flux of curl F across this surface will be equal to the circulation along the boundary. So that's what this relation says. The first integral is for circulation along C, and whereas the second integral is for flux of curl F. Okay. Now when it comes to divergence theorem, which says that flux across the surface which will be equal to divergence inside the volume. So that's what it says. It means flux across the surface will be given by this integral f bar dot ds, or people may write it as integral along the surface f bar dot n cap into ds. Okay, so this is the formula for flux. Now the divergence theorem says that this flux across a closed surface will be equal to divergence inside the volume, that is divergence of f into dv over this. Okay, so let me write it here clearly. So this is equal to triple integral over E divergence of f bar into dv. So flux across the surface will be equal to divergence inside the volume. Okay, so problems on the divergence theorem will be very easy when the divergence is constant. For example, let's take this question. Let's say you are given f bar equal to xi minus 2j plus 5k, not minus 2j, minus 2yj plus 5zk. This is what f bar is. Now the question is, what is integral along S f bar dot ds? What is it where S is a sphere. S is a sphere that is given by x square plus y square plus z square equal to 25. Given it is a closed surface, sphere, it means it is a closed surface. When it is a closed surface, I can apply divergence theorem to find flux. So first let me see what is the divergence of the vector field. Divergence of f bar. Divergence of f bar is nothing but dou by dou x into x plus dou by dou y of minus 2y plus dou by dou z of 5z. Now its derivative is 1 minus 2 plus 5 This is nothing but 4. So divergence is a constant. Now our life is easy. Therefore, from divergence theorem, from Gauss divergence theorem, I can say integral along S f bar dot n cap into ds, which is equal to triple integral over E divergence, that is 4. Or let me write one step. Divergence of f into dv. So that's what triple integral over the sphere. This is 4 into dv. This is nothing but 4 into volume of the sphere. Here the integrand is constant. So integrating over that solid, it is same as finding the volume of the solid. So therefore, this is nothing but 4 into volume of the sphere. What is the formula? Saying 4 by 3 pi r cube. Yeah. So now this is 16 by 3 pi into r. Radius is nothing but 5. So 5 cube. So this is 16 times 5 cube, which is 125 divided by 3 into pi. So this is the answer. Okay. So when the integrand is constant, you can directly write that constant into volume of the given solid. But if it is not constant, there is no escape. We have to evaluate that integral. Okay. And one more thing, suppose if f bar is given by, see, we know one relation. The relation is nothing but divergence of curl f bar is 0. Suppose if f bar, anyway, for a given vector field, we always calculate divergence to apply Gauss divergence theorem. If this becomes 0, answer will be 0. Then there is nothing to discuss. Okay. So this is about divergence theorem. So you do one thing, you go to the previous questions, the previous gate questions. Like you'll find questions on Gauss theorem, Stokes theorem. You may not find more, but on Gauss divergence theorem, you'll find more questions. So on Gauss divergence theorem as well as Green's theorem, and then there will be some questions on directional derivatives or finding unit normal vectors, and then what are the other topics? Some questions may be asked on operators, like the relation between divergence, curl and gradient, that they may ask. From where else? Yeah, line integrals and conservative vector fields. So most of the questions will come from these parts. Okay, so please spend time on previous questions so that you will get some confidence. Right. So I'll stop it here.